This is probability lesson number 5. It's called binomial distribution. A binomial distribution is a type of probability distribution. So what is a binomial distribution? In the first orange box here, this is very important, the information that's contained in here. Like it says, these are the essential elements of a binomial distribution. The four main points are that there must be a fixed number of trials. We'll call those n. Each trial has only two possible outcomes, a success or a failure. It's important to note there too that it doesn't mean that there's only two outcomes. There can be multiple outcomes, but the outcomes can be characterized as the thing that you're looking for being the success, and then everything else being its complement or the failure. All right. The third point, the probability of success, we usually call it P, is a constant from trial to trial. So again, that leads into the fourth point, which means that they must be independent. So if it's a case of drawing marbles from a bag, they have to be replaced. All right. The parameters that define unique binomial distribution are the values of n, the number of trials, and p, the probability of success, and that's the probability of success on each trial. Obviously stays the same. And the notation that you're going to see representing a binomial distribution is given here. And that is simply read as x is distributed, that little tilde symbol there, is x is distributed binomially with n number of trials and p probability of success. And again, at the bottom, this paragraph is worth reading. The binomial distribution represents the distribution of the number of successful outcomes of a binomial experiment. Could be something like tossing a coin to get a heads. Could also be things like rolling a dice, finding the probability of getting a 2 on a certain number of rolls. Again, 2 would be your success. Every other number would be the failure. Where there is a known number of trials, the number of tosses or the number of rolls, and the probability of success in each trial is known. Therefore, something like probability of heads would be 0.5, obviously. So if the coin is tossed 3 times, the binomial distribution gives the probability of getting 0, 1, 2, or 3 heads. And at this point, it might be worth just showing this again as a probability distribution table. I like to represent these in a table format. Kind of helps in solving problems. Okay, so here, tossing a coin 3 times, we've done the example before, but the different outcomes that can happen is on 3 tosses, there could be 0 heads observed, 1 heads observed, 2 heads observed, or 3 heads observed. So don't forget that in conducting this experiment a certain number of times, you also have to consider that the event that you're looking for may not happen at all. In the case of 0, if you draw the tree diagram for it, what you'll find is the probability of getting no heads. I'll just draw the tree diagram above here quickly. So we have heads and tails, heads, tails, heads, tails. And here would also be heads, tails, heads, tails. Tails, tails. And again, the probability on each of these branches is 1/2, right? So you're going to multiply 1/2. So each of the outcomes has a probability of 1/8. Now, the probability of getting no heads would be all tails, for example. You could have represented that with the complement of h as well. That would work. But anyway, we also recognize that no heads means all 3 tails, and that probability would be 1/8. The probability of getting 1 heads, all right, you'd have to follow through the branches that have only 1 heads. You would find that there's 3 of them. So that probability is 3/8. The branches that have 2 heads, that result in 2 heads, is also 3 of the 8. And then the branch that has all 3 heads is just the top branch. And again, it has a probability of 1/8. And again, what you would have to notice here is that the probabilities in the table do add up to 1. And again, that has to be true. It's the same as what we just talked about with the probability distribution tables in the last lesson. All right, so here again we see the notation. X is distributed binomially with n number of trials and p probability of success. This scenario can be represented with a formula. The formula is in your formula booklet. And in the orange box here, you should recognize the formula. It looks very similar to the formula from the binomial theorem. It is just slightly different. What you'll notice is that in the formula here, P is the probability of success, and R is the number of successes. Okay. So really what it is, it's the NCR. So N is the number of trials, R is the number of successes that you're looking for, and then you're multiplying by the probability of success raised to the number of successes, multiply that by the complement of the probability of success. So in other words, the probability of failure raised to the number of failures. Okay, that's really what that notation is showing. And sometimes we can replace the 1 minus P with Q, for example, and then the formula reduces to NCR of the probability of success raised to the number of successes, the probability of failure raised to the number of failures. Okay, where P again is probability of success, Q is the probability of failure. All right, and now we'll do the example. So in the question, they're giving you the information that X is distributed binomially with 5 trials. The probability of success is 0.6 on each trial. What the question's asking is find the probability that X equals 4. So in other words, what's the probability that there are 4 successes? All right. So the way to calculate this, using the formula, is the probability that X equals 4 is equal to, and we'll just substitute into the formula, it's 5 trials. We're looking for the probability of 4 successes. The probability of success on each trial is 0.6, and we're raising it to the number of successes. And the probability of failure is then 0.4, obviously, has to be the complement, and it's going to be raised to the 1. A lot of the same rules apply in this formula as do in the binomial theorem formula. Some of the exponents have to add up to n. Okay. And if you perform this calculation, you get 0.2592. All right. I'll also show you at this time, it's coming on the next screen, but I'll also show you how to calculate this using your calculator. There's a function on the calculator that calculates this very easily. It's called binomial, it's binomial distribution function, but there's 2 of them. The one that we're going to use for this calculation is PDF, and I'll just give the syntax of the entries. The first entry is number of trials. The second is the probability of success. And then the third is the number of successes. So now to enter that would be binom PDF 5, number of trials is 5, the probability of success is 0.6, and the number of successes that we're looking for again is 4. And I'll show you how this calculation can be performed using a calculator. So to start with, you're going to second vars, distributions. It's faster to scroll up. It's binom PDF that we're looking for. Option A. And if you have a new operating system, it'll give you the prompts. If you don't, you'll have to enter it according to the syntax that I showed you. The number of trials, though, is 5. Probability of success is 0.6. The x value means the number of successes that you're looking for. In this case, it was 4. And then you'll just paste into the main screen, hit enter, and you'll see that the calculation is 0.2592. You notice, or if you noticed in the when we went into the distribution menu, there was 2 options of binom function. One was binom PDF, one was binom CDF. The way I determine which one I'm using, again, the question here was asking the probability that x equals 4. For me, I think of that as a particular probability. And so I use binom PDF. We'll see in a little bit here when we use the other. On to the next slide. All right, so here's a page that shows you how to do these various calculations. All right, the first one, again, is similar to the one that we just did. We're told that x is distributed binomially with number of trials 4, probability of success is 0.25 on each trial. Find the probability that x equals 3. So that, again, is a particular probability, so we would use binom PDF. Okay, and again, you can either go back in, or you can just go second enter, and you can redo the last, just change the parameters. So 4, this is 0.25, and we're looking for the probability of 3 successes. And just hit enter. 0.046875, there it is. Okay. In the next part, in part B, we're told that the probability, that x is distributed binomially, with number of trials 4, again, probability of 0.25. But this time we want to know the probability of all the outcomes of x being less than or equal to 2. All right. So this is a range of values now that we're looking for. Okay. The way I like to represent this, again, is with a table. All right. And I'll just put the table here. Again, all the various outcomes on four trials would be that none of these things might happen. 1 might happen, 2, 3, or 4. It might happen on every trial. Okay. And what we're looking for in this question is, what's the probability that the value will be less than or equal to 2? So really what we're looking for is we're looking for all of this. And really what this is, the way I think of this is it's cumulative, right? So we want to add up the values of the probability of x being 0, the probability of x being 1, the probability of x being 2. We want to add all those up. And so the function that we're going to use in the calculator is the binom CDF. All right, so it will accumulate these probability values and add them. So what it does is it calculates the probability of x being 0, calculates the probability of x being 0, the probability of x being 1, or the probability of x being 2, and it adds up all those 3 probabilities. Okay, and the way that calculation is done, I'll just enter it in here. It's shown in these screenshots on the side, but I'll just write it here as well. So probability of x being less than or equal to 2 is equal to binom CDF, again because it's cumulative. Again, but now the entry is going to be the number of trials still, so 4, probability of success on each trial, 0.25, and I want to add all the way up to 2. Now this is important, all right? So as we keep going through here, you're going to see how we adjust these cutoffs, all right? But we do want to add all the way up to 2, and including 2. So this would be our entry. So we'll go back into our distribution menu, scroll up, and now just go to binom CDF, option B, hit enter, asks for the number of trials, which we know is 4. Probability of success on each trial, again, is 0.25. and we want to stop when x is 2. So we want to add up to 2. Paste it in, hit enter, and there it is, 0.949. Three significant figures. Same as the calculation in the screenshot. All right, now the next one is, again, the information is the same. X is a distributed binomial with four trials. Probability of success is 0.25 on each trial. Now find the probability that x is greater than or equal to 3. So using the same table as above, with the same outcomes, 0, 1, 2, 3, 4. Notice I don't really put any values in for the probabilities. That's not really what I'm looking for here, because I'm doing it by the calculator. But now what we're asked to find is the probability of the number of outcomes being 3 or greater, right? Greater than or equal to 3. So we want these. Now the other thing that's really important for you to know here about how the calculator does this is that the calculator adds from the far left. All right, so it always adds from 0. You can't change where the calculator starts to add from. All right, so what we have to do is we have to manipulate how the calculator is going to perform this. I only want the values 3 and 4. Now I could go ahead and I could calculate the probability of 3 and the probability of 4 using binom PDF and then add those, but that's a bit longer process. The way we're going to do it, and again it's shown right here, the note, okay? What we're going to do is we're going to add up the probabilities 0, 1, and 2, or we're going to let the calculator add the probabilities 0, 1, and 2, and again, using our knowledge that the sum of the probabilities from 0 to 4 have to add up to 1, we're going to take the sum from 0 to 2 and subtract it from 1, and that will leave just the sum of 3 and 4. So the way that calculation would look would be the probability that x is greater than or equal to 3. It's written right above. I'll just write it here. Is 1 minus, it's going to be binom CDF. And again, the entry will be 4. Number of trials is 4. Probability of success is 0.25. And again, now you have to be careful again about where you tell the calculator to stop adding. You do want the calculator to stop adding at 2. We want to remove all of this in red. So we want the calculator to add up to 2, calculate that, and subtract it from 1. So again, the way that that's going to look on the calculator, you can just enter it this way. Go 1 minus, start it here, then go into your distribution menu, go to binom CDF. Again, the number of trials is 4, 0.25, 2, all of those values are still the same for us. Again, paste that in, hit enter, right? And there you get the answer, 0.0507 or 0.0508, I guess. Which again is just the complement of the answer that you found in part B. All right, next question. Example 3. Records show that 6% of the items assembled in a production line are faulty. A random sample of 12 items is selected at random. It says with replacement, it wouldn't necessarily have to. The assumption here is on an assembly line, there's probably thousands of items being manufactured. And so removing 12 items doesn't appreciably affect the probability of these outcomes. So in a case like this, it doesn't necessarily have to be stated that it's with replacement. So what we want to do is we want to find the probability now that none will be faulty. All right. And again, the things that could happen here on taking your 12 items are your 12 trials now, right? And so things that could happen here are these. By removing 12 items, none of them could be faulty, or 1, 2, 3, so on, all the way up to 12. All 12 of them could be faulty. So that any of these numbers of outcomes are possible. All right. The first question, part A, asks the probability that none will be faulty. So really what we're looking for is the probability that x is equal to 0. All right. Again, this is a particular probability, so we can just simply enter binom PDF, all right, and it is 12 trials, probability of success on each trial. Again, success in this case is that it will be faulty. That's a success, okay, and then 0. And if you do this calculation, our trials will be 12, probability of success 0.06, and number of successes that we're looking for is 0 in this case. Paste it in, and you'll get the answer 0.475. Okay. Part B asks, at most one will be faulty. So the notation for that is probability x is less than or equal to 1. That's at most. All right. So now what I want to do is I want to add up the probability of none being faulty or the probability of 1 being faulty. But again, we can do this all in one step with the calculator function. We can use binom CDF. Again, it's 12 trials. Probability of success on each trial, 0.06. And we want the calculator, now the 1 that we enter means we want the calculator to add up to and including 1. So our calculator entry will look like this. We'll go second, vars. I think we can go alpha B. No. And we can go 12.06, 1, enter, and then that probability is 3 significant figures, 0.841. Now in C, the probability at least 2 will be faulty. Well, at least 2 will look like this. At least 2 is x greater than equal to 2. So in this case, what we're looking for is we're looking for the probability of everything more than 2. All right, so we're looking more than or equal to 2. Sometimes I just draw a line straight across. And again, in this case in particular, you wouldn't want to add up each of these probabilities individually from 2 to 12. That would take a long time. So again, what we want to do is we want to use the calculator efficiently. And so what we're going to do here is we're going to do, I don't want the values 0 and 1, and I know the calculator starts adding from 0. Okay, so it will add 0 and 1 in order. So I want to subtract those two. So from 1, so I'm going to enter 1 minus binom CDF. And my entry will be 12, comma, again 0.06. And now I'm telling the calculator where to stop adding. I want it to stop adding at 1. So again, we'll enter this in our calculator. It'll be 1 minus, go to the distribution menu, alpha apps key does it nicely. All of these values are the same. Enter, enter. And we get the answer 0.160. Okay. And then in part D, we're looking for the probability at least 1 is faulty, and at least 1. This is very This is a very common question. Very commonly asked question. At least 1 means that x must be greater than 0. Okay? X is greater than 0. That's the definition of at least 1. X must be greater than 0. Now, something that you should write, because you get a point for it on an IB exam, is the first thing you should write for this is this is the complement or the opposite of x not happening, x equaling 0. So if you write 1 minus px equals 0, that shows that you recognize at least 1 is the complement of none happening, and you'll get at least a point for that in most cases. But our calculation now will look like this: 1 minus binom CDF, and again the number of trials is 12. Probability of success on each trial 0.06. And we want the calculator to stop adding at 0. Actually, in this case, you can use either binom CDF or binom PDF. Both will work. And again, this calculation is also you can do it fairly simply with the binomial distribution formula. All right. We'll just do it with the calculator here. So it's going to be 1 minus second. And we're going to go alpha apps. These entries are all the same. But I do want the calculator to stop adding at 0 this time. Enter. You should get the answer 0.524. Is that probability. All right. Moving on. Next slide. Fourth example. There are 2 blue marbles in a bag of 10 marbles. If a marble is selected, it's color noted and then returned to the bag. How many trials does it take so that the probability of getting at least 1 blue marble is greater than 0.95? Okay. Again here, I'll draw the situation. Okay. So on each draw, we can either get a blue or not a blue. And again, notice this is a bag of 10 marbles, but we've reduced it down to only 2 things happening. It's either the success, which is the blue marble, or the failure, which is not a blue marble. All right? We know that the probability of drawing a blue is 2 out of 10, so 0.2. So the probability of not drawing a blue then has to be 0.8. All right? And so what we want to know is we want to know how many times we have to draw so that the probability of getting at least 1, or the complement of none, if you want to think of it that way, is greater than 0.95. So what we'll do is we'll just extend the branch where it's none, all right? And again, probability stays the same each time. Now, notice in the first case, the complement of not getting a blue is 0.2, all right? So that doesn't match. That's not greater than 0.95, okay? But notice as we extend along the branch, all right, what we do is we keep multiplying the probability of not getting a blue, which is 0.8, by raising it to the number of trials. All right, so the second time we raise it to 0.8. So the probability of not getting a blue at this point is actually 0.64. All right, so the probability of getting at least 1 is the complement of this, which would be 0.36. Okay, so the probability of x being at least 1 would be 0.36. If we do it again, probably not blue, again it's 0.8. And if you multiply 0.64 times 0.8, it's 0.512. So at this point, the probability of not getting all 3 blues is 0.512, which is still fairly big. So the probability of all the other outcomes, that's what I'm showing here by the line above. Everything else is at least 1 blue, all right? Only this bottom branch is no blue, all right? So now the probability of x being greater than or equal to 1 is, again, 1 minus the 0.512. which would be 0.488. So really what we want to do is we would extend this, and we want to know when the probability of x being greater than or equal to 1 is bigger than 0.95. All right? So the way we'd set this equation up, or this formula up, is we're saying the probability of x being greater than or equal to 1 is equal to, it's always equal to 1 minus the probability of x equaling 0. There's the complement, or the opposite of at least 1, is 1 minus the probability of that event not happening. All right? And again, what we want this to be, we want the probability of x being greater than or equal to 1, we want that to be 0.95. Okay? And we want to know after how many trials will that happen. Now, the calculation of the probability of x equals 0, you notice, is always just 0.8 raised to the number of trials. For the first one, it was 0.8 to the 1. For the second one, it was 0.8 squared. For the third one, it was 0.8 cubed. So this can be given as, we don't know which number of trials it'll be, and this will be 0.95, so it'll be 0.8 to the n. And obviously it's an exponential equation. And really what we want here is we want this to be an inequality. We want this to be greater than 0.95. We want that probability to be greater than 0.95. So we'll use the inequality in there. And so now what we'll do is we'll rearrange it. It's obviously exponential, so we'll use logs to solve. So we have I'll move things around, so we'll have 0.8 to the n will be less than, it's going to be 1 minus 0.95, which will be 0.05. And using logs to solve, we'll have n log 0.8 less than log 0.05. And we're going to divide by 0.8, log 0.8 on both sides. Realize that log 0.8 is a negative value, so we're actually dividing by negative on the left. So that'll force the inequality to change its direction. It's going to be log 0.05 over log 0.8. And that value calculated, n is greater than 13.4. So in answer to our question then, how many trials will it take so the probability of getting at least one blue marble is greater than 0.95? I'll have to say number of trials before it'll be bigger than 0.95 must be 14. Okay, obviously n has to be greater than 13.4, so the next value is 14. All right. And then on to the next example. We can also do expected value with the binomial distribution. It's very easy with the binomial distribution. You don't need to use the table. It's simply, if you look in the orange box, the expected value is simply given by the number of trials times the probability of success on each trial. Again, you can only use it if you know that the scenario is a binomial distribution. So in the example 5, it says on the day of the math test, the probability of a student being absent is 11%. If 73 students sit the next math test, how many students can be expected to be absent? Expected value then is number of trials, probability of success on each trial. The number of trials, again, is the number of students. In this case, the probability of success is the percentage, 0.11. If you do this calculation, it's 8.03, which we would say is approximately 8 students. Okay? Very, very easy, very straightforward calculation once it's a binomial distribution. And on to the last example here. So we have a tennis player who finds that he wins 3 out of 7 games that he plays. If he plays 7 games straight, find the probability that he will win each of these different scenarios. And again, remember that I'll just draw the table up here for this situation. Again, don't forget all the possible different outcomes that could happen out of 7 games is that he might win none. 1, 2, 3, 4, 5, 6, or 7. All right. So in part A, the probability that x equals 3, again, that's a particular probability that we're looking for. You can calculate it using the formula. It would look like this. It would be 7c3. The probability of success is 3/7 raised to the number of successes, would be 3. And the probability of failure then has to be the complement, 4/7 raised to the number of failures. Well, if he wins 3 of his 7 games, it means he has to lose 4 of the 7. So if you perform that calculation, or if you do binom PDF of 7, 3/7, and 3, all right, all these should give you the same answer of 0.294. That's rounded to 3 significant figures. In part B, at most 3 games, so at most 3, it could be 0, 1, 2, or 3, not more than 3, at most 3. And so that notation would be given by the probability that x is less than equal to 3. And that again would be given by the calculator function of binom CDF. And again, we want the number of trials, 7. Probability of success on each trial is 3/7. And we want the calculator to stop adding at 3. And again, that answer, if you put in the calculator, is 0.653. That's the probability. In part C, all 7 games. So again, it's the probability that x equals 7. Okay. Just notice, if you use the formula, this is what you end up with, right? It would be number of trials 7, number of successes that you hope to see would be 7. Probability of success is 3/7, raised again to the number of successes that you're hoping for, which would be 7. The complement, or the number of losses, probability of losing, would be 4/7, raised to the number of losses, okay? Which really just reduces to 3/7 to the 7, okay? Or again, you can use the binom PDF function on the calculator, but this is fairly easy. It becomes 0.00266, I guess. And 0.00266. In part D, I'm going to change the question a little bit. Let's change it to more than 4 games. Okay, so change that. Just so we have a variety of questions that we're answering. So the probability of winning more than 4 games, again, is the probability that x is greater than 4. Right? Again, using the table that we've made here. All right. More than 4 games has to be 5, 6, or 7. All right. And the way that we would do that calculation then would be, again, it has to be complementary, so it's 1 minus binom CDF. And again, what we want the calculator to do is it's 7 games, probability of success, 3/7 on each game. But we want the calculator to add up to and including 4, so we want it to stop at 4. We don't want any of those from 0 to 4 included. Okay, and if you do this calculation, you get 0.1266. In part E, okay, at least 1 game. So here's the at least again. Very, very commonly asked question. So the probability that x, again, is greater than or equal to 1, again, is equal to 1. Again, write this down when you have at least 1. 1 minus the probability that x equals 0. And again, 1 minus binom, either PDF or CDF will work with 0. Okay, and so it's 7, 3/7, and 0, and that probability is 0.980. Question F, the expected value is equal to NP. Sorry, the question says, after playing 30 games, how many would he expect to win? So his number of trials is 30. Probability of success on each trial is 3/7, and so that would give us an answer of 12.9, which again you may interpret as approximately 13 games. So out of 30 games, you might win approximately 13. I just wanted to add one question to this with this same scenario. I'll just go on to the next page here. And that is, we'll make it G, and we'll use the wording at least 3, but no more than 5. Okay. So again, if you use the table, all the outcomes are these, 0 to 7. Okay, I'm playing 7 games. All right. What I want to calculate is at least 3, so that's 3, 4, and then no more than 5, so I stop at 5. So I want these 3 values in the middle here. And again, I want to use the calculator to do that. The way I'm going to do that is this technique. So what I'm going to do is I'm going to get the calculator to add up all the probabilities up to 5, all right? And then I want to subtract off all the probabilities up to 2. And hopefully you can recognize then that the probabilities that are left are 3, 4, and 5. So the way I would do that calculation is this. The probability of x being between 3 and 5, I would do binom CDF, the bigger amount, okay, so it would be 7 trials, probability of success 3/7, up to 5, minus the binom CDF, again, add up the probabilities, 7 trials, probability of success 3/7, and I want the calculator to add up to 2. Okay, so just you can perform this all in one line. So again, using the distribution feature in your calculator, you want this to now to be 7. You want this to be 3/7, and you want to add up to 5, the first part. And then we want to subtract. And again, I'm going to go into the distribution. Same number of trials, same probability of success, but I only want to add up to 2. I want the calculator to stop adding at 2. I'll paste this into the equation and hit enter. And that probability would be 0.613. All right? Another favorite type of question that might be asked. All right, go ahead and try some of these homework questions on your own now.